Bam! Mr. Tarrou. In this algebra lesson, we are going to be defining and looking at the graphical attributes of linear absolute value functions. And through the lesson, we are going to, well, be defining what a linear absolute value function is right over here. We're going to be ultimately doing we're going to be doing 3 examples where we create the graph of this absolute function, just using a t-table, not anything real fancy, not with transformations, which is a lesson we're going to be doing probably right after this one, graphing absolute value functions using our knowledge about what the parent function looks like and our knowledge of transformations, and we'll develop that knowledge together, of course, in the lesson, but we'll be doing these with just t-tables. And once the graphs are set up, specifically the second and third example, we're going to be looking at those graphical attributes. Where's the function increasing and decreasing? Are there any absolute max or mins? Are there, well, I don't know, what's the domain and range and such like that? Okay, so the definition, or just simply what is an absolute value function? And the absolute value function is identified by a pair of straight lines. They're kind of like a grouping symbol. Like parentheses or brackets, but the fact that these grouping symbols are these long straight lines on each side of an expression, well, what does that say? When you take the absolute value, of a number, the answer is the distance that number is away from 0. So the absolute value function gives us a distance. Now, a distance, here's an old yardstick. Okay? It goes from 0 to 36 inches. It's measuring, in this example, length. And really kind of like this is a number line, where this is x on the number line, and we're just dealing, or 0, and we're just dealing with all the positive values, all the numbers to the right of 0. Well, when we deal with negative numbers in mathematics, you see like -2, -4, -6, -8, those numbers are indicated as being negative because they're on the left side of 0. So when I take the absolute value of 4, I had a direction, I had a thought there, but I'm going to stop and go on with this for a second. The absolute value of 4, well, here's 4 on the number line, and let's, well, I don't know, put an orange star on that. So here is 4. That is 4 units away from 0. The number 4, as I count back, 1, 2, 3, 4. Okay, so 4, positive 4, is 4 units away from 0 on the number line. Well, if I come through here with a green star, and I say, all right, well, where's -6? -6, well, we need to understand that on a number line with the 0 in the middle, moving to the right are the positive values, and moving to the left are the negative values. So -6 is 6 units to the left of -6, and I kind of just did the absolute value there. 1, 2, 3, 4, 5, 6. So here is, well, we can see -6. How far is -6 away from 0? Well, I just actually counted the distance off, didn't I? I said 1, 2, 3, 4, 5, 6 units away. So when I was counting how far -6 was from 0, I was actually taking the absolute value of -6. That's what we're getting, how far a number is away from 0 on a number line. Now, in real-life applications, negative numbers, when you buy a car, especially any car really, but especially like a brand new car, as soon as you sign the paper and drive it off the lot, the value of that car depreciates, goes down very drastically. So you can have a negative balance on a car. You can owe more than it's actually worth. Or really just owing money in general is considered a negative value. If you owe someone $10, then that would be indicated as your value would be well, -10. You owe 10, but if you had $10 in your pocket, that would be a positive $10. Think of, maybe if you've never dealt with money, that might be maybe not a good example. Think about altitude. If the altitude of sea level, or when you're at sea level, water level, that altitude is said to be 0. But if you have a positive altitude, like, well, where I live is about, I think, maybe like 50 feet above sea level. So that would be a positive 50 feet. But if you, go to the ocean and you start swimming underwater, maybe you're swimming a few feet under the surface of the water, then your altitude would be -3 feet. So you're still 3 feet from the surface of the water, or like where I'm living, I think it's about 50 feet above sea level. Those distances are positive, but saying -3 feet indicates that you're 3 feet below the level of the surface of the water. So the signs are indicating some type of movement, a direction. And the absolute value function gives us a distance. And distances, there are no negative numbers on this yardstick because, well, there's no such thing as a negative distance. It's a negative indicating direction. Okay, I hope I didn't ramble on there too long. Now, if we look at the absolute value of negative 8 plus 5, some students will want to incorrectly get rid of both of these negative symbols and write 8 plus 5 and then get an answer of 13. But we don't want to do that. You want to, with absolute value functions, you want to simplify the expression that's inside that absolute value function first. So the absolute value of negative 8 plus 5, well, okay, let's see, back to the number line. Negative 8 is negative, or 8 steps to the left, so here's negative 8, starting from 0, negative 8, and then positive 5 is 5 units to the right. So 1, 2, 3, 4, 5 is landing us at, well, 3 units to the left, or 3 spaces to the left of 0, so we're landing at negative 3, or, it's the absolute value of negative 3. I'm not sure how comfortable you are with, adding numbers with different signs. If you don't have a number line, if you're combining numbers with different signs, you subtract those numbers and keep the sign of the largest absolute value, and the absolute value of 5 is 5, and the absolute value of negative 8 is 8. 8's bigger than 5, but 8 originally was negative, so you keep the sign of negative 3. So now that we've simplified the expression inside the absolute value function, the absolute value of negative 3, well, here's negative 3, and it's 1, 2, 3 units away from 0. So the absolute value of negative 3 is 3. The absolute value of negative 8 plus 5 is equal to 3. Okay, so I don't know if, just a little review of absolute value function if you've never seen that before. The family of linear absolute value functions includes functions in the form of f of x is equal to a times the absolute value of x minus b plus c, where a, b, and c are real numbers. So these are all variables the way it's written in general form, but we'll see, potentially some number of, 2 and 5 and I don't know, negative 1 here. And if we don't see an a, it's going to be assumed to be 1 because multiplying by 1 doesn't change the value of that product. Adding by 0 doesn't change a product or doesn't change your sum. So if the c is 0, you won't see it actually there, but that would assume, you could assume it to be 0. And it's called a linear absolute value function because the expression inside the absolute value functions is a linear polynomial. That's in algebra, that's all we're going to be dealing with. You can have all kinds of functions in an absolute value symbol. You can have cubic functions where you have a polynomial, sorry about the phone, with a degree of 3. You could have a quadratic where a degree is 2. You can have, like in this case, we're going to be specifically looking at linear functions where we have a polynomial. We gave a good definition of that in the previous lesson. Similar lesson, only it was about quadratic functions, but let's see here. Polynomial functions, at least especially in algebra, will only be dealing with one independent variable, and all of the exponents will be whole numbers. You can't have negative exponents or decimal exponents for it to be a polynomial. They can exist in different equations, but we have different names for them. So we're going to graph y is equal to x plus 2. Now, I'm doing a lot of review. I hope you're enjoying this as we go through it and it's not too boring, or I'm not going over too much stuff you already know. My algebra book that my school has purchased and is working through, some of this you haven't been exposed to. So I'm kind of elaborating more than maybe what is in my book because I've seen other books where the sequence of these concepts are different. So please excuse me if I'm going over too much that you already know. We have y is equal to x plus 2. Well, we have a slope, our coefficient in front of the x because y is by itself. But by the way, this is in the form of y is equal to mx plus b, slope-intercept form of a line. We have a slope equal to 1. Slope is rise over run, so we're going to rise 1 and run over 1. And the constant off by itself is b, and we're looking here, 2. And so if I graph this without doing a t-table, our y-intercept is 2. Again, y equals mx plus b. Our slope in that specific form, our slope is the coefficient of x. So we're going to rise 1, run 1, make a new point, and sketch this line, which this isn't graph paper, so it's not going to be perfect, but looks something like that. That's the graph of y is equal to x plus 2. Okay, why am I graphing a line? I mean, hello, I'm supposed to be talking about absolute value functions. Well, that idea that we see here that's why I kind of did these arithmetic examples. The absolute value of negative 6 is positive 6. Negative 6 is 6 units away from 0. The negative sign just indicates direction. So you kind of want to just say absolute value functions, get rid of the negative. I mean, that's what a lot of teachers say, and you kind of forget that it's a distance that you're getting from 0. So if I come in here now and I bring in the idea of an absolute value function, picking a color I haven't used yet that will stand out, hopefully orange will from the red. If I want to graph y is equal to the absolute value of x plus 2, and kind of going back here with this arithmetic example, I hope I didn't make an error, the absolute value of negative 8 plus 5, well, negative 8 plus 5 came out to be negative 3, and then we took the absolute value of that and we got positive 3. So we can have negative numbers inside the absolute value function, and we can keep those negative numbers in there as we simplify. But once we simplify to a single term, this has two terms, separated by addition and subtraction, we take that absolute value, and it kind of does get rid of the negative sign. So y, if y is equal to, and all we have on the right is the absolute value of x plus 2, this as a final answer will never be negative. We cannot have any negative y values from that expression. We'll never have any negative dependent values. So, okay, so every place I put my point, my chalk, is going to be represented by a coordinate, x and y coordinate. Like this point here is 1, comma 3, because from the origin move right 1 and up 3. This has a coordinate of 0, 2. This has a coordinate, I think, of negative 1, 1, if my sketch is fairly accurate. This has a coordinate of 0, excuse me, not 0 first. My students make that kind of mistake all the time too sometimes. Left and right movement first. So negative 2, 0. And now if I come into here, that coordinate is going to be negative 3, negative 1. So I'm plugging negative 3 into here. Negative 3 plus 2 is negative 1, but the absolute value of negative 1 is positive 1. So with that absolute value sign wrapped around, or function wrapped around the x plus 2, the portion of this line that is going to have negative y values is going to get reflected around about the x-axis and look like this. Okay, so what I just did here was I'm trying to pull your information, your knowledge about, if you have been introduced to it, you know already, I hope so, about graphing lines in slope-intercept form, introducing this new function of an absolute value function and showing you, at least in this example, again, in the next lesson when we do graph any of these absolute value functions with transformations, we'll make it a bit more sophisticated and give you some slightly quicker ways of graphing these functions, but we're just going to do them with t-tables. They're going to have some kind of a bounce, and that bounce is going to create, that sharp bend is going to be created from, like I just showed you there, the portion of the functions that would have otherwise been below the x-axis. That absolute value symbol, getting rid of those negative answers, is going to reflect it about the x-axis and give you a sharp bend, and, well, at least in this particular example, seem to, you know, as you read it left to right, bounce off of the x-axis. A lot of absolute value functions will bounce off of the x-axis. If there's a plus c, when we learn about transformations, if there's a constant, an addition or subtraction outside of the absolute value function, we're still going to have a sharp bend somewhere in the graph, but it is going to not be necessarily on the x-axis. Okay, so that's a rundown of how what absolute value functions give you, how graphically they look compared to just graphing regular linear functions. And this was about looking at the graphical attributes of linear absolute value functions. So let's get out of the way, do one more example like this, only with a t-table, show you how to make a graph with a t-table, and get to defining those graphical attributes. Alrighty, we are going to graph with a t-table. Y is equal to 2 times the absolute value of x minus 3 plus 1. And once that graph is up here, we are going to be looking for intervals where the function is increasing, where that function is decreasing. We're going to be looking for any absolute maximum or minimums if they exist in the graph, and then identifying domain and range. And I'll also, when you're graphing absolute value functions, whether they're linear absolute value functions or not, you want to, if you're doing a t-table, identify where is the sharp bend going to be. Now you won't, maybe not necessarily the entire coordinate of the sharp bend, but the x-coordinate of the sharp bend. The sharp bend for these absolute value functions are going to occur at the x value that makes the inside function, the inside expression, what's inside those absolute value symbols, equal to 0. So first thing we're going to do is we're going to come off to the side. I'm going to look at just the inside part of this, x minus 3. We're going to set it equal to 0 and solve for x. Well, with the x on the left-hand side of the equation, we have a minus 3. The opposite of minusing 3 is adding by 3, because I want to move that 3 over the equal sign over to the other side of the equation. 3 minus 3, or negative 3 plus 3, of course, is going to be 0. So we have x is equal to 0 plus 3, which is 3. This is going to be the x-coordinate for the sharp bend, that sort of pointy part of the graph. So we're going to set up a t-table. X and y is equal to, actually let's do it this way. 2 times the absolute value of x minus 3 plus 1. And when we get done putting our independent variable into our expression, we're going to get the output value, the dependent value of y. And if your book's using function notation, that'll maybe say f of x in place of y. Now that we know what the x-coordinate of where the sharp bend is going to be, we're going to let that be the sort of the middle of the column for our values of x. And then we're going to count, and if this we're looking at the number line, we're looking at an x value of 3. We're going to count to the left and then count to the right. We're going to use some smaller numbers and some larger numbers in our t-table. And at least with these linear absolute value functions, there's going to be symmetry of the graphs, like you saw a little taste of that in the previous lesson. I'll have a link to that one in the description of this lesson, or if you look at my playlist, you'll see them in order as I teach them. They'll have some symmetry in the graph. So if we go back and count by, you can count by 2s, 1s, 3s, whatever you feel like. I'm going to count back by 1. So 3, 2, and 1. And so 3, 2, and 1. Then we're going to count to the right, 4 and 5. If you space out your values of x evenly like that and have them centered on that x-coordinate where the sharp bend is going to be, you're going to see the same answer show up in your t-table, and that's a way to check your work to make sure that you're not making any mistakes. Now what I'm going to do now is we're going to take each of these x values, and I'm going to write the expression and not even look at the number that I'm plugging in case I'm plugging in a negative value. Sometimes that helps avoid any kind of sign error. So I'm going to write 2 times the absolute value of something minus 3 absolute value again plus 1. That something is going to be equal to 1. We're going to work out the arithmetic for this and get a value of y. So maybe, you know, in some scratch work we've got over here, I'm going to erase this, but we're going to have 2 times the absolute value of 1 minus 3 is negative 2 plus 1. The absolute value, now I can't do 2 times negative 2 because the negative 2 is inside the absolute value function. I need to work that out first. So the absolute value of negative 2 is positive 2. Notice that I'm writing parentheses now instead of the absolute value function because I've applied the absolute value function. I've found the distance that negative 2 is away from 0, or just got rid of the negative sign. And I don't want to put a little x for multiplication because it looks like a variable x now that we're doing algebra, and so I'm using parentheses. 2 times 2 is equal to 4, plus 1 is equal to 5. Now I'm going to repeat this process, and I don't think you need to see me talk through 4 more additional points. I'm going to step off and reveal the work for each of these 4 other points, and then afterwards plot the points. So far what I'm looking at is, again, we have an x-coordinate of 1 and a y-coordinate of 5. So with this being my xy axis and each of these tick marks representing a value of 1, let me put a 2 and a 4 there to indicate that. We're going to go to the right one for the positive x-coordinate of 1, and then up 5. 1, 2, 3, 4, 5. And that is the first point in the process of creating the graph of this linear absolute value function using a t-table. Let me step off and reveal the rest of this work and get back to, answering these other questions. Okay, so we got all the points up. I showed you the steps of how to find this with quite a few of those. You saw that I showed the work on finding the y-coordinate when x is equal to 3. Again, I told you expect that symmetry, and I got the same y value of 3. Actually found the same y value of 3. That's to check my own work. And if I got 3 and 5, then I knew something was wrong with my arithmetic on one of those two lines, and then I could go try and find it. Now to connect these dots, if this were a quadratic function, a polynomial with an exponent of 2, and knowing then that the graph would look like a parabola, then maybe I would want to put some kind of smooth, try and draw a smooth curve somehow between these lines. But if I was using graph paper and being real accurate, I might realize that didn't seem to be working because, well, this is a linear function inside this absolute value function, or a linear expression inside the absolute value function. And thus, these graphs, if that's linear, are going to be made up of straight line segments where there's some kind of sharp bend at that, in this case, x coordinate of 3, because 3 is what makes the inside expression equal to 0. Now, where is the function increasing? Where is it going up to the right? Where are the dependent values increasing while the independent value increases? All sounds all fancy. Where the y's get bigger as x get bigger. And again, focus on the interval along the x-axis. The function is increasing from either x is greater than 3, if your book is using inequality notation, or if your book is using interval notation, you'll see that it's increasing from 3 to infinity. Now, all of my textbooks say that that a function is increasing or decreasing on an open interval. Some textbooks will say that it's that they can increase and decrease on a closed interval, and if that's the case, your text might have an equal sign here and a square bracket instead of a round parentheses indicating that greater than symbol as opposed to greater than or equal to. I'm being consistent with my textbooks. Where's the function decreasing? Where as x increases are the y values decreasing, or whereas the independent variable increases, the dependent variable decreases or goes down to the right. And that's going to be the intervals from, well, there's only one sharp bend, so it's going to be decreasing where x is less than 3, or from negative infinity all the way up to the left side of the number line, negative infinity, because this is going to go up and to the left forever, or come down to the right forever, from negative infinity to 3. Again, if your book is using interval notation as opposed to inequality notation. Identifying the absolute maximums or minimums. Now, is there an absolute lowest y value or an absolute greatest y value? And there can be relative mins and maxes as well. I'm just using the language that's appropriate for where I am in my algebra book at this time, that my school is using. The graph goes up forever. So this arrow means that as I go up to the left or up to the right, the y values are just going to keep getting bigger and bigger and bigger and bigger and bigger forever. So there is not a finite largest y value in this graph, but there is a smallest y value in this graph. The lowest point in this graph is at the y value of 1. So there's an absolute minimum. Okay, I'm not going to have the room to write it. So there's an absolute minimum of 1. And I like my students to identify where that absolute minimum is. That's the minimum. It's a minimum of 1, but it's at x is equal to 3. Okay, so all linear absolute value functions will have one interval at least in the form of y is the dependent variable and x is the independent variable, that form that was on the previous screen. All absolute value, linear absolute value functions in the form of y is equal to a times the absolute value of x minus b, close the absolute value symbol, plus c. They're all going to have one interval where the function is decreasing, and one interval where the function is increasing. Okay, sorry for the static there. They're also going to have either an absolute maximum or an absolute minimum, but they're not going to have both, as we discussed about, there's an absolute bottom minimum value, but not an absolute max because it goes up forever. The domain. What is the domain of the graph? Now that we have the graph drawn, what values of x is included in this graph? Well, this graph is made up of an infinite number of points, and each one of those points has their own unique x-coordinate. So the domain, as you see it expand forever, and there's no breaks in the graph, I could draw the whole thing without ever picking up my piece of chalk or your pencil. The domain is all real numbers. You might see it written. You might see a double R. If your book again is using interval notation, it will be from negative infinity to positive infinity. If you're using inequality notation, it might be x is greater than negative infinity and less than positive infinity. I don't know what book you're using. The range values, well, my x is going on forever. My range values, what y values, what dependent values are included in all the points that we see represented by this graph? Well, the smallest y values we've already discussed is a y value of 1, and then the graph goes up forever. Now, y range has something to do with y, but not the y-intercept. All the different y values that are in these coordinates that make up that graph, and there's an infinite number of these coordinates that are making up that absolute, infinite number of points that are making up that absolute value graph. And the smallest y value included is 1. So the range is going to be y is greater than or equal to 1, or if, again, it's in interval notation, square bracket now because of the equal sign, 1 to infinity. All right? And that is one good example of graphing absolute value functions with a t-table, how you want to go through it, finding the x value that makes the inside expression equal to 0, make the center of your t-table, and then go a little smaller, a little larger. And we do have, just hinting about what we're going to take a really good close look at later on in our studies, we have this line of symmetry where we can see that it's sort of like a mirror image. If I could fold this over, the graph would exactly line up on itself, and we see that in the y values of our t-table as well. And I'm pausing because there was one other thing I wanted to mention, but I don't remember what it was. Oh, yes I do. Look at my absolute value function. It's got a sharp bend on it, but it's not on the x-axis. That is because of this plus 1 that's not inside the absolute value function. That plus 1 shifted the graph up. A little preview of what we're going to learn later, graphing absolute value functions using transformations. I got one more example. Now, the next example, I'm going to put it on the board. I'm going to just sort of give you an opportunity to pause this lesson and try one of these problems completely on your own. I'm going to just talk at the very, very end. I'm going to put the problem up, I'm going to reveal the solution one step at a time, about every 5 seconds or so, reveal another step, and then when it's all said and done, you can check your work and I'll go over anything that I think maybe we need before finishing up this lesson. No. I hope you got that right. We took the inside expression, set it equal to 0. We worked out this two-step equation to find the x-coordinate where the sharp bend occurs, which is 4. moved a little bit lower and a little bit higher on my list of x-coordinates, counting evenly so that I can see these matching y values show up and check my work with that idea, that property that all linear absolute value functions will have, which is some symmetry there. And we then therefore had intervals or increasing intervals where the graph goes up to the right everywhere past the x-coordinate of 4. So our increasing interval is x is greater than 4, making our decreasing interval everywhere where x is less than 4, or there are answers in, again, interval notation. Once I was done with this example, I was like, why didn't I make another example that opened up? That gives us an absolute minimum of 0 at 4. The domain, again, is all real numbers because that graph opens up forever. I can draw the entire thing. Well, I said that before, I can draw the entire graph without lifting my pencil, but that doesn't automatically mean the domain is all real numbers, so scratch that. And the range, there's no graph below the x-axis. There's nowhere down here. There's no graph that includes points that have y values which are negative. The smallest y value is 0, and then the graph goes up from there. That is the range of that graph. Now, a couple of key points before we're done. I know this video is getting a little long, my lesson's getting a little long, but they all kind of do because I try and, highlight some points of interest in places where students might have some issues. I said earlier that absolute value functions, they are grouping symbols, but they're not just a grouping symbol. They give you ultimately the distance a value is away from 0. But some students will see this. Maybe I should write it in red because it's technically wrong, what I'm about to do. Once students learn how to undistribute or factor out monomials, if you've been exposed to that or studied that yet in your math studies, some students will look at this and they'll want to take this -2 and bring it outside of that absolute value symbol, working with it as it's just a straightforward grouping symbol, where -2 divided by -2 is +1. And +8 divided by -2 is -4. That is not correct. That is not allowed. These absolute value symbols are not just a grouping symbol. They're a mathematical function that is an operation that needs to be done. And we basically just kind of took the -2 right out of there and never applied that absolute value function to it. You want to leave your -2x plus 8 in that absolute value function. And just leave it like that. Okay, you could even, maybe you could do it this way. There's no real reason to do that unless you have studied, like we'll do in an upcoming lesson here soon, about graphing absolute value functions using transformations. There's really no reason to do that. Okay, but actually, just to finish this up really quick, yeah, right, me doing something really quick. If I wanted to give you a little bit of a preview, and I'm going to do a lesson, and I'll have a link to that lesson after I do it in the description of this this video, graphing absolute value functions using transformations. If I just introduced a little negative right in front, outside of that absolute value function, that negative would have carried through all of these steps of arithmetic, and I would have had to simplify what was inside the absolute value function, take the absolute value of whatever's in there, and then multiply it by -1 as I follow my order of operations, and that would have made all my y values negative. And that leading coefficient in front of this entire function, which was negative, would have, if I had done it, reflected. Now this is, well, I don't want to use red again because I just said, that might be for when I'm doing an example that's wrong. That would reflect, like if there was a negative right there, that would have reflected my graph down instead of being above the x-axis, below it. And by the way, you should know what a function is by now, the difference between a function and a relation. And I have been saying the word function a lot in this lesson, and if you did forget that, or again, I don't know what book you're using and what teacher you have. If I draw a vertical line through this graph, each of those vertical lines representing an x-coordinate, like maybe This is the x value of 1.5. A function is such that every x value is only mapped to or connected to or related to one particular y value. Or in other words, when I draw a bunch of vertical lines, they're only going to cross the graph once. That's what a function is, and that's what this video is about. Defining the graphical attributes of linear absolute value functions. I'm Mr. Tarrou. Bam! Go do your homework.